Hi guys, welcome to the second screencast on recovery. So we're still going to be looking at Epoc, or excess post-exercise oxygen consumption. So the focus of today's screencast and next lesson is going to be the slow component. So part 2 of recovery, which again is a slow compartment. So just a quick recap on last lesson, looking at the fast component or the lactic acid component of Epoc and recovery. First of all here, so the main focus we looked at was the duration and alongside how it allows the replenishment of blood and muscle oxygen stores, as well as the resynthesis of the ATP and PC system. So that's what we went through during yesterday's lesson. Today's focus, as I said, is on this slow component, and the key kind of information that we're going to be doing are on looking at duration, looking at this elevated circulation, elevated ventilation, elevated body temperature, and this lactate removal and conversion to glycogen. Now this is going to be our focus, specifically concentrating on this lactate removal or lactic acid removal and conversion of lactic acid into glycogen, which we're going to go on to in more detail when we get there. And then this process will eventually allow us to get the energy back following the exercise we do, and it's all due to this excess post-exercise oxygen consumption. This we're going to be looking at later on in the year. So first of all, just getting the graph back up that you should be aware of in terms of this is the fast component, so the lactic acid component part 1, and then we've got this here which is the lactic acid or slow component part 2. So again, as we've already stated, when we exercise, certain things deplete. So we have this depletion of ATP and PC stores and oxygen from myoglobin that we get back. Now this we looked at in yesterday's lesson, and the focus on today's and the slow component is going to be this glycogen here, and it's also what happens to this lactic acid that we get here. Now with regards to the fast component in blue here, colour coordinated, looked at the ATP and PC system and how it's replenished via endothermic reactions, and then obviously oxygen from myoglobin, we looked at how oxygen creates or binds with hemoglobin to make oxyhemoglobin, and how oxygen also binds with myoglobin at the muscle to make oxymyoglobin. And so today's focus is this stuff in red, which is the slow component. So we should be aware now that you know how this is going to work with regards to kind of like memory method here. So we've got what, how ratio 1, 2 and 3. So this is focusing on the slow component, which is known as the lactic acid recovery part, and it's part 2 of Epoc. So first of all, it's the second slow component of Epoc that I've already discussed. Now the key function, so what is the key function of the slow component is to remove lactic acid and replenish glycogen stores. That's our real key focus for today. So the how, now this is really important. So the how is, so post-exercise lactic acid readily converts back to pyruvic acid. Now it's really important to realise we look at lactic acid as a harmful substance, as something that we don't want. However, when oxygen is present and comes into the system, lactic acid can actually be a benefit. So two things happen when we go into lactic acid converting back to pyruvic acid. We either get the pyruvic acid being oxidised, or we get it converted into glycogen. So if you remember the glycolytic system here, we get glucose and we get pyruvic acid into lactic acid. Well, when oxygen is present, lactic acid likes to convert back to pyruvic acid, and then when it's present, oxygen, we get two things happen. Pyruvic acid becomes oxidized, and then also we get it's converted to glycogen. So second how, as I've just said, the pyruvic acid is either oxidized or it's converted back into glycogen. Now we need to know the ratio of how much pyruvic acid is oxidized and how much is converted into glycogen. So ratio 1, 60% of pyruvic acid is oxidized into the Krebs cycle. This is, remember, post exercise. Now this is during Epoc, so 60% of pyruvic acid is oxidized into the Krebs cycle, and this produces CO2, H2O that we sweat out, and energy. So that is one part of what happens to pyruvic acid. It is readily converted, the lactic acid is readily converted back to pyruvic acid, and 60% of this is oxidized into the Krebs cycle. CO2 is breathed out, H2O we sweat out, and then we get energy. Ratio 2, you've got approximately 25 to 30% of pyruvic acid is reconverted into glycogen to be stored in the muscle and liver, and glucose to be put back up or topped up in the blood. Now, it's really important here, if you can see there's just a mistake here, don't write this part down yet, I'll explain what's going on here. So when pyruvic acid is converted into glycogen to be stored in the muscle and liver, it is known as glyconeogenesis, so this should be a Y here. Now I understand this is a term that you haven't come across before. Now you just need to attack it, okay, so it's a long kind of complicated word. Don't worry about it too much, you just need to ensure that you kind of understand that this is when glycogen is converted from, or pyruvic acid is reconverted into glycogen. So this is called glyconeogenesis, so that should be a Y. This is stored in the muscle and liver, and then glucose is reconverted, or pyruvic acid reconverted into glucose via gluconeogenesis, and that's to be topped up with blood glucose levels. So you've got glyco for glycogen and glucone for glucose, and then it's just neogenesis at the end. So that's 30% of this pyruvic acid is reconverted into glycogen, glucose via glyconeogenesis or gluconeogenesis. Finally, ratio 3, we get 10% of pyruvic acid is converted into protein, and this is removed via sweat and urine. Okay, so that is kind of lactic acid and removal and replenishment of glycogen stores. Now, in terms of the next part, so oxygen is required to fuel Epoc. Okay, so you should know now that the fast component requires between 1 to 4 litres of oxygen. It's really easy to remember this slow component because from 4 you've got 5. So what we need with regards to the slow component, oxygen we need is about 5 to 8 litres. Okay, so the slow component of Epoc uses approximately 5 to 8 litres of oxygen. Now, these elevation parts, you've got oxygen elevation 1, elevation 2, elevation 3. You need to have this down the side of your paper here. And we need to make specific kind of specification reference to the elevation of these 3 things. This will really help our recovery process. So we have elevated ventilation or breathing rate, i.e. how much we're breathing, is elevated ventilation. Now this allows the 5 to 8 litres of oxygen required that we need for the slow component of Epoc to be successful. So breathing in deeper, heavier, faster, that gets to 5 to 8 litres of oxygen required. Okay, this elevation 2 is to do with circulation. Okay, now circulation, you've got to think about like increased heart rate, increased stroke volume, increased cardiac output. Now we've done quite a lot of work on this in the past, and this is kind of it bringing it all together almost. So with this elevated circulation and elevated ventilation, what we get, so both of them together, it allows us to deliver oxygen to the working muscles. It allows us to remove carbon dioxide, more carbon dioxide. It allows the removal of lactic acid via pyruvic acid, which we've just spoken about, and then it also allows us to maintain our venous return. Remember, venous return is the amount of blood going back to the heart. Now this is really good to stay elevated and maintained because that is going to have an increase on, or an effect on, our stroke volume, cardiac output. It means we're getting more blood moved around the body, which prevents blood pooling, that gives us our DOMs that we experience, all the real aches and pains you get after exercise. So far, elevation 1, ventilation, elevation 2, circulation. Finally, elevation 3 is to do with our body temperature. Okay, now this allows our metabolic rate to continue to increase. Okay, so this means basically it's got here which allows the body to continue breaking down glycogen and fats to produce energy. What we have to understand is basically with the metabolic rate being increased, it means we continue to break down glycogen and fats in our aerobic system, which allows us to produce energy to allow us to recover. I hope that makes sense. So with this kind of energy being produced from the aerobic system, it is allowing us to recover, breaking down these kind of burning these calories, breaking down the glycogen and the fats via the aerobic energy system. So ensure that you've got all that down. Then finally, the last thing we need to know is the time, so the process of this full recovery. Now the slow component can take 1 hour. However, depending on the intensity of the exercise, it can actually take up to 24 hours. So obviously the more intense, the harder you've worked for, it's going to take longer to recover. So the slow component of Epoc takes approximately 1 hour to 24 hours, depending on the exercise intensity. When you're making your notes or developing your questions, please make it specific to elevation 1, elevation 2, 3, so on, time, okay, duration, etc. Please make sure you do that. So make solid notes on these, and I'll see you in our next lesson. Thank you. Bye.